Okay, let's begin with the exercise 5 checkpoints. There are partial derivatives. We are considering field. Field means a function that is whose argument is a position. This position is all over the space. And it may depend on time too. It depends on time too, then it is a time dependent field. It is nothing to do with the mathematical word field. Mathematical word field is for algebra, a set of numbers that has some operation, something like addition and multiplication. But in physics, field is a function of a spatial component, spatial position. And if it also depends on time, it is time-dependent field. If it is independent of time, we say it is a time-independent field. Whether it is time-dependent or time-independent, it is always dependent on position. The position consists of three Cartesian components, x, y, z. So we have to consider the derivative with respect to x, y, z separately. So partial derivative is simple. It's a derivative, but because the function is a multivariable function, it depends on x, y, and z. So if I take the derivative with respect to x only, then I say it is a partial derivative with respect to x. That means keep y and z the same and vary only x component. So this is a x partial derivative. What about the y partial derivative? X, z, z. They are the same, but I vary x only. The z derivative vary z only. Understood? So it is there is no difference. What you learned in high school, it is just single variable function, that is the df x, that is f of x plus epsilon minus f of x divided by epsilon as the limit epsilon goes to 0. So this is the same, but we have multivariable function in physics. It is also possible to take a double derivative, but for example, I can take the derivative of f by x twice. However, it is also possible to take the derivative with respect to x and y one by one. This is there is a mistake. Not a mistake. It is the same. So answer is D. This, for example, f of xy equals x times y. If I take the derivative with respect to x, then this answer is y. If I take the derivative of y, then this is dy over dy, that is 1. On the other hand, f of xy equals xy, and I take the partial derivative with respect to y first, then coefficient is x. And then I take the partial derivative with respect to x later, then it is 1. They are the same. Okay? If it is a differentiable function with respect to x and y both, in that case, this derivative and this derivative, they commute. It doesn't care about the order of derivative. Y first and then x next. X first, then y. They are the same, remember. Leibniz rule comes from the total derivative this identity. If I divide by dt, then the derivative of product is derivative of the first one multiplied by the original function of the second one, and so on. In a similar manner, I can generalize this one to many other cases. This one, f a1 e1, a2 e2, a3 e3. So if I take the derivative, then I have f dot a plus f a1 dot e1, a2 dot e2, a3 dot e3. Therefore, it is f dot a plus f a dot. So it can be generalized. Again, a dot b Cartesian component expression is like that. So I can make use of this derivative rule repeatedly to find that scalar product of two vectors, its derivative is in this form. Sure, I can also apply the method to the cross product of any two vectors. So a times b, but I put the derivative of the first and second and so on. If I have triple scalar product, I need to add, oh, this is wrong. I need to write down a cross b dot c, a cross b dot c, a cross b dot c, then put a, b, and c. This is the answer. Okay? The single variable function total derivative is the derivative of this function multiplied by the differential of this. So when we integrate a function that is a function of a variable t, then total differential is independent of that one. So it is a much more convenient form. I can always change the variable from t to any other useful, more convenient variable using this method. Remember, this is next one. F is a function of x and y, then it changes by varying this one is different from this. And this change is proportional to this. And this one has additional piece, small pieces. In the limit, delta goes to 0, the other components vanish completely. And this one from this one, I can say here dx is delta as delta goes to 0. So with this one we say differential. By taking the differential, this finite delta approaches 0, arbitrarily close to 0. So I can find the identity. The remaining piece, everything goes away. In a similar manner, the change in this function happens also through the variation of y. Something like that. In a similar manner, that amount is this one. As a result, the total differential, that is infinitesimal change in function, that is function of x and y, then partial derivative with respect to x multiplied by the x differential. Partial derivative of f with respect to y multiplied by y differential. And add them up. Then this is the total differential. We can extend this idea to n variables case. Then the total differential of a function is the sum of these. Every partial derivative with respect to all of the independent functions, independent argument, and multiplied by this one. They are the same. So, for example, if we have a three variable case x, y, z that we usually have to compute, it is x derivative dx, y derivative dy, and z derivative dz. Then it is total derivative. For example, I can say total derivative xy, this is dxy, and y dx. Let's see, what is that? This is understood? This is, therefore, it is aha. Understood? What happens to the case dxyz? That is yz dx, z x dy, xy dz. And this one is actually derivative, partial derivative with respect to x. This is a partial derivative with respect to y. This is partial derivative with respect to z. So this is all right. So everything is clear. This is already we have studied. Chain rule can be employed the differential of this. That's fine. dAB, A dB. What happens to, we have a dA dot B equals A dot dB plus dA dot B. In that case, if I substitute A with B for B, then it is A dot dA dot A. And they are commutative. It is a 2A times dA. Aha. dA squared, dA vector squared equals 2 times A dot dA. That means A dot dA equals 1/2 dA squared. It is a very important. We will compute this one more than 100 times. Very useful identity. This is wrong. This is vector 2 is missing. One of the reason why we frequently use Cartesian coordinates is they are invariant. So independent of time. So the derivative of the unit vectors, they are all 0. The first derivative vanishes, so second order derivative also vanishes. So, you know, A dot equals time derivative of A, and A dot dot, double dot, is second order time derivative of A. So apply these previous results to compute the velocity, and velocity is a sum of these 3 components. And unit vectors, Cartesian unit vectors does not have time derivative, so they are still here. Only the coefficients x1 dot, x2 dot, and x3 dot appear. In a similar manner, I can take the double time derivative. Still, the unit vectors of the Cartesian coordinate, they are invariant. So there is no time derivative because they all disappear. So only the Cartesian component has double time derivative. So it is very simple. In any coordinate system, the velocity acceleration can be obtained by taking a single and double time derivatives of the components of the position vector respectively. And this is the nature of Cartesian coordinates. Basis vectors are independent time only in Cartesian coordinate. We will find it is not true for this polar coordinate system. In polar coordinate system, it doesn't work. So this is true only for the Cartesian coordinate. All E1, E2, E3 are invariant, but if we use polar coordinates, they vary depending on the angle. So we derive the basis vectors in 2-dimensional polar coordinates using 3-dimensional vector. Okay, on the XY plane, theta, this unit vector along the radial direction, this is, as we know, this is ER hat, unit vector along the radial direction. Angle theta with the x-axis and 1/2 pi minus theta with respect to y-axis. If I take the partial derivative with respect to the radius, then this is constant and this is a constant. So only I take the derivative of this, and remaining piece is this one. And this is ER hat. Because it is proportional to ER hat, but magnitude, you can find the magnitude cosine square theta plus the sine square theta equals 1. So that's the reason why this one is ER hat. What happens to the angle derivative? It should be proportional to E theta. If I take the derivative, cosine becomes minus sine, sine becomes cosine, and I have over a factor r. That is the radius. And I need to, the magnitude is a square square, sine square, cosine square, plus 1. So I have a additional over a factor. So I need to divide this one to find that this is E theta. E theta is this one. What about the z derivative? They are independent of z, and z derivative is a simple one. So, that's right. This is E3 hat. So I have found 3 unit vectors of this. Actually, this is actually the cylindrical coordinate system. I just have shown these at 1 and r. That's the reason why I have divided by magnitude of this vector. This is radial vector. It is a tangent vector. And this is along the z direction. Just like E1, E2, and E3, the ER and E theta, this is E1, theta, theta, E2. ER, E theta, we remember this one. Just like that, R theta and E3, they satisfy this triple scalar product. So orthogonality of the 3 basis vectors is preserved on the rotation about the z-axis. So it behaves like ER is something like E1, E theta is something like E2 after rotation, and E3 is the same as E3. It is invariant. Only this set has been rotated. All these are the same as what we learned for something like that. Okay. Find the false statement involving the ER, still ER and E theta. Let's see. DER minus E1 hat sine theta d theta plus E2 hat cosine theta d theta. So what we find is something multiplied by d theta. And what's that? This is E theta. DER equals E theta d theta. Additionally, dE theta is ER d theta, but we have negative sign on it. The reason is that we have a circle. ER is here, E theta is here. If I rotate by a very small, tiny amount, that is a d theta, this amount of change, that is parallel to E theta. Understood? And the amount is, this radius is 1. What is the arc length of radius r? Radius r equals 1. This is r d theta, and r equals 1. So this is d theta. So magnitude is d theta, and the direction is e theta. So e theta d theta is the change of infinitesimal change of a unit radial vector. In a similar manner, in geometry shows this is in this direction. And actually this is along, this is ER, this is minus ER. So when you rotate E theta, what you get is minus ER. Again, this arc length is d theta. So minus ER d theta is that one. So that's the reason why we have a differential of E theta is proportional to E minus ER. And the proportional constant for the differential element is d theta. If we are equipped with this relation, then what we have to do is just divide by differential time. Then it becomes dER over dt equals ER dot. This one becomes E theta d theta over dt. This is E theta theta dot. Okay? This is the dot. So this is this. This is this. But there is a negative sign missing, right? So ER is invariant under the variation of R, right? ER, this one is a 0 because there is a no R appears. If I take the derivative with respect to R, it is a 0. The reason is that ER, origin, ER. If I change the radius, still ER is the same. ER changes the direction only when I change the angle. Okay, we have 10 minutes break. Okay. Any questions? 질문 있어? 질문하려고? 그가 뭐야? D가 이거의 차이가 0이 아닌데 이것이 델타 곱하기 F 프라임 이거하고 같진 않은데 델타를 0으로 보내면 이것이 F 프라임 데피니션이 델타분의 F x 플러스 델타 빼기 F x 이렇게 되잖아. 델타를 빵으로 보내면 이게 F 프라임이 되지. F 프라임이 dF 오버 dx 이렇게 된단 말이야. 그런데 같지 않다라는 것이 이 델타의 제곱, 세제곱, 이 찌끄러기가 델타를 0으로 보내면 다 없어진다는 거예요. 양변을 델타로 나누면 x 플러스 델타 빼기 f of x 델타 이렇게 되고 여기는 f 프라임이 나오고 그 다음에 델타 제곱이라 델타 제곱 그래서 리미트 델타를 제로로 보내면 얘가 다 없어져. 그래서 미분이 나오는 거야. 아하, 그러니까 0으로 가는 리밋에서는 요것을 df라고 이름을 짓자. 그러면 df 나누기 dx는 f 프라임 이렇게 쓸 수가 있으니까 그 함수 f의 변화량은 미분에다가 x의 변화량을 곱한 거하고 같다라고 치자. 여기에 틀린 부분이 있는데 그것은 이 small d라고 하는 것을 씀으로써 그 델타가 0으로 가는 것을 내포하고 있기 때문에 이거는 의미가 없다. 오케이? 그런데 이게 한 개의 변수일 때는 이렇게 쓰는 거고 두 개일 때는 f를 바꿀 수 있는 방법이 x를 바꾸어서 변화를 시킬 수가 있고 y를 바꾸어서 변화를 시킬 수가 있고 이걸 다 더한 거를 하자. 오케이? 그리고 그게 n개 있으면 x1, x2 이렇게 해가지고 n개까지 그냥 단순 무식하게 extend 한 거지. 그것을 어떤 것으로 알 수 있냐면 x 더하기 1의 제곱을 하면 x의 n제곱을 미분한다라고 하면 이것은 x 플러스 델타의 n제곱 빼기 x의 n 이렇게 쓸 수 있잖아. 그럼 이거 전개를 하면 x의 n x의 n-1 델타 플러스 n-1 2분의 x의 n-2 델타 스퀘어 이렇게 나가잖아. 그치? 여기서 이걸 xn으로 빼버리면 요가 날아가 버리고 이 전체를 x 플러스 델타의 n 빼기 x의 n 델타 이렇게 해버리면 nx n-1만 델타가 없고 나머지는 2분의 n-1에 x n-2가 있는데 여기 델타가 있고 델타 제곱이 있고 그럼 이 델타를 0으로 보내면 얘가 다 없어지지. 그래서 우리가 x의 n제곱을 미분하면 nx의 n-1이라는 걸 얻지. 오케이? 그래서 델타를 0으로 갈 때 이걸 갖다가 아예 이렇게 쓰자. x 플러스 dx의 n승 빼기 x의 n은 이거는 f x의 미분에다가 dx라고 하자. 이거야. 왜냐면 이 dx의 제곱, 세제곱은 다 날아가 버리기 때문에 0으로 다 날아가 버리기 때문에 그냥 이렇게 쓰면 된다는 거죠. 오케이? Okay. So if I take the derivative, because we know der equals e theta d theta, I put dt in the denominator to find it er dot equals e theta theta dot. In a similar manner, e theta dot equals, because de theta equals minus er d theta, the answer is minus er theta dot. er double dot equals er dot's time derivative. Okay, er dot's time derivative, er dot is here, e theta theta dot, that's the time derivative. So e theta dot plus e theta theta double dot, and what is that? This minus er theta dot square plus e theta theta double dot. Acceleration is always toward the origin. Here, if theta double dot equals 0, then er double dot equals minus er theta dot square minus er. So in uniform circular motion, theta dot equals omega, that is constant. In that case, this tangential acceleration disappears and centripetal force is toward the origin. Any uniform circular motion has acceleration toward the origin. This one shows, and that is minus omega squared. If I multiply the radius, constant radius r is a constant, then x double dot equals minus r omega squared er hat. That means minus r omega squared. Magnitude is r omega squared, and direction is minus er hat toward the origin, the centripetal force. So x dot equals RER. X equals R times ER, radial direction. And time derivative, that is R dot ER plus R ER dot. ER dot equals E theta theta dot. So R dot ER plus R theta dot E theta. Aha. Circular motion, tangent, this is radial velocity. Radial velocity. And it is a tangential velocity. That is R theta dot. Along the direction of E theta, it is a R theta theta dot. And usually we use theta dot as omega. R omega is the tangential velocity. So in uniform circular motion, R is constant. So R dot equals 0. So radial velocity disappears in a circular motion. In the circular motion, omega equals theta dot. Okay, V equals R theta dot is R omega. And we need to return to the same position after we travel 2 pi r. This is the distance. Distance divided by velocity is time. Two pi r divided by velocity, r omega. That is 2 pi over omega. That is the period of uniform circular motion. X equals RER here. And if I take the time derivative twice, I have this result. And this one can be ER dot equals E theta theta dot, E theta dot equals minus ER theta dot. Substitute. So you will find this result. And this is a radial acceleration. This one, R omega squared. This is a centripetal acceleration. This is a tangential acceleration. And this is related to Coriolis acceleration. Tangential, centripetal acceleration, radial acceleration is composed of this is radial acceleration. And this is centripetal. This is all radial. Okay. Omega cross x. We set omega to be E3. Cross product R ER. We remember R theta E3. That is one. This ER E theta equals E3, E theta E3 equals ER, and E3 ER equals E theta. Just like E1, E2, E3, E2, E3, E1, E3, E1 equals E2. So E theta ER, that is E theta. So R omega E theta. Aha, this is what we know. This is a tangential velocity. Tangential velocity in a uniform circular motion, tangential velocity can be interpreted as omega cross x. And what about omega cross x dot? X dot, this is x dot. Tangential velocity is obtained in the uniform circular motion. And so we have omega cross r, omega cross x. So this is x dot. So the last class we learned the back cap rule. Back cap rule. What's that? A cross B cross C equals the back cap. So omega cross x. Omega A is omega. B is omega. B is omega. And C x. Let's see. X is on the xy plane. X is RER. And omega equals omega E3. They are perpendicular. So this one disappears. And we have minus omega squared x. Aha. Omega cross. Very useful. Now, indefinite integral, yes. For example, integration of x squared dx, for example, then I would rewrite this one as a d, 1/3 x cubed. So the answer is 1/3 x cubed. What is that? This is f. And what is this? This is integral df. It was dx df dx integral. So now you have noticed that why I keep find the total differential of a function. It is complicated. It is very simple. And if I copy this one, this is the final result. So that's the reason why I keep finding total derivative of function. This is very important. Here, what is the total differential of this? This came from EAX over A. So after integration, the answer is this. You usually memorize this the fast track computation, but in the middle, you put this step, then life will be much easier than high school. The step of integration is actually you need to find the total differential of a function. That's the key point. But you have never been trained to find the total differential until now. But from now on, please find, and when you evaluate the integral, please find the total differential first. Then everything is very simple. And if you want to verify your calculation, simple way is take the derivative of this. This is wrong. This is wrong. Xn plus 1 over n plus 1. This is wrong. (13). This is the integration by parts, and I believe you are familiar with the integration by part now. So let me just pass. This is I told you previously, very important. X dot x, this result. In fact, it is x dx, y dy, z dz. This is 1/2 of dx squared, 1/2 dy squared, 1/2 of dz squared. And actually this is 1/2 of d x squared y squared z squared. That is 1/2 integral d 1/2 of x vector squared. In a similar manner, you remember arc sine, that is inverse function of sine. From here to there, minus 1/2 of pi, from half of pi, if we cut this one, we can find the inverse function. Inverse function is this one. And this is arc sine. And this is sine. And defined in the region minus 1/2 of pi to half of pi. So because you know how to compute the derivative of sine, sine's derivative of cosine, right? So using that relation, you can find the inverse function derivative. And inverse function's derivative is just flip the numerator and denominator, because we have a symmetry of these two functions. So y equals x, that means exchange in x and y. The inverse function is in the graph, exchange x and y, and exchange x and y, then you find the dx over dy. So if you find the derivative of a function, then the derivative of the inverse function is just to flip the numerator to denominator and denominator to numerator. They're very simple. And you must have learned in high school. So using that formula, you will find it is easy to compute the arc sine. And this is a binomial expansion. You will find this arc sine can be evaluated if you expand this one in powers of t when t is less than 1. And this is a binomial expansion. This is not, this is true for any real number. Any real number. It is true for example, square. That's fine, but it is also true for 1/2. It is also true to minus 1/2. Very useful. Only if this expansion converges. For example, if you substitute 2, it fails to converge. It should be in this region. Anyway, I don't ask you to follow all these calculations. This is a demonstration how this expansion works. And I have explicitly computed with this formula exactly. This is quite accurate. You can find a better way to find the convergence as fast as possible. So that is the work for mathematicians. But anyway, I'd like to tell you how these numbers can be approximately obtained in practice. Next, we evaluate the circumference of the circle. You memorize this, the 2 pi r. This radius is r. The circumference of the circle is 2 pi r. But let us compute this explicitly. We have x equals r cosine theta and y equals r sine theta. And we can find this is x comma y. This is x plus dx, y plus dy. This is the distance. Distance is x dx squared plus dy squared. The length, dl. And what we want to compute is integrate dl. That means integrate this function over the circle. So in here, I need to know this value, right? But I have a constraint, x squared y squared equals r squared. So x 2x dx 2y dy differential equals 0. Aha, dy over dx equals minus x over y from this identity. But we know the symmetry. These all 4 are the same. So we simply compute this and multiply by 4. This one in here, xy equals r comma 0 is 0 comma r. So I want to integrate over x from 0 to r of this function. And that function is actually this one, and we substitute r x equals r cosine, y equals r sine, substituted in here to find it as a integral. That is just angle. So this final result is 4 pi r. Another way to evaluate area of a circle, I can make use of these polar coordinates. Area of this some element with radius dr wait a second. R, dr, and we have theta here, theta plus d theta. So why don't we compute this area and sum them over? And if you take the d theta goes to 0 and dr goes to 0, they become, this is the dr, and this is a radius r, so arc length is r d theta. Okay, so this d theta dr. So what we want to compute is r d theta dr integration over angle is 0 to 2 pi, and the radius is 0 to a, and this is 1/2 of a squared, and this is 2 pi, so pi a squared. But how can I find this one to be this area? The reason is that DRER hat, this is the displacement along the radial direction, and displacement along the theta direction is r d theta e theta hat. That's what we know. And they are perpendicular. Cross product is 3. So drr d theta e3 hat. This is the area element, and direction is always perpendicular to the xy plane. This is proportional to z-axis. That's the reason why we were able to compute this area of a circle. We can extend it to compute the volume of a sphere. That is extended to the three-dimensional case, and we end up with the surface of the sphere and volume of a sphere. You have to compute by yourself, following the reason why I keep telling you this triple scalar product to find the volume is to let you evaluate this curved surface area and volume. That's it for today. 질문 있어요? 이번 시간에 배운 내용이 어렵다고 생각하지 말고 반복해서 학습을 해야지. 이것이 영원히 2학기까지 나오고 하여튼 수학이나 물리 문제 푸는데 항상 대학교 수준에서는 그 공면과 그 공면이 내포하고 있는 그 부피 이런 것들의 아주 단순한 그 기초적인 계산이기 때문에 이 단계를 넘지 못하면 너무너무 괴로워. 그래서 여기는 정말 열심히 반복해서 완전히 암기할 정도로 해야지 돼. 내가 여러 번 얘기했지만 어려운 것은 어려운 것이 아니라 여러분들이 암기하지 않았기 때문에 어렵다고 생각할 뿐인 거야. 내 손으로 해봐서 반복하면 암기가 돼. 이해가 안 되면 암기를 하고 여러 번 풀면 구구단을 여러분들이 암기했지 이해했나? 그런데 일생 동안 구구단을 써보면서 나중에 그 속의 깊은 뜻을 많이 알게 되지. 그런 식으로 생각해. 그거를 어렵다고 생각하고 이게 수학이 아니라 산수야. 이건 그냥 세물 할 뿐이야. 부피가 한 컵, 두 컵 물을 합쳤더니 물의 부피가 얼마가 되니 이런 문제는 물리에서 맨날 풀어야 하는 것이기 때문에 이걸 수학을 공부해서 뭐 누구한테 물어봐서 아니. 여기 다 써 있으니까 꼭 반복 학습을 해야 된다라고 하는 거 여러분들이 꼭 기억해야 돼요. 질문이 없어? 질문이 없다라는 거는 관심이 없다라는 건데 벌써 나가네. 오케이. 수고했어요.
교수님,
그
X5에서요.
잘 안 들려.
아, 그럼 혹시 나중에 메일로 드려도 될까요?
잘 들려 이제.
그 X5에서 그 포물선 하실 때요.
X5 어디쯤이야?
5.5요.
5.5. 5.5가 요거? 여기 몇 페이지야?
5페이지예요.
5페이지. 여기?
네. 거기서 그 중력 가속도를 그 2투로 하신 게 2차원이셔서 2투로 하신 거예요?
그거는 내 마음이지 뭐. 여기 그냥 그림에 XY를 이렇게 잡았네. 이렇게
네.
잡으면 얘가 요거의 마이너스 2 방향이 되는 거고. 그치?
네.
뭐 E3를 잡아도 되고 그거는 문제를 풀 때 좌표계를 잡는 것은 아무 상관이 없기 때문에 항상 뭐 그거를 이게 E3가 돼야 된다라고 암기하면 안 되고 상황에
네.
따라서 좌표계가 어떻게 주어졌느냐 없으면 내가 내 마음대로 잡으면 되죠.
네, 감사합니다.
음.